Let's say that we had a function defined by the infinite series. So we're going to go from n equals 1 to infinity. And each term is going to be x to the n plus 1 over 4 to the n times n to the fourth. And we could even expand this out. When n is equal to 1, this is going to be x squared over 4 times 1 to the fourth. So it's just going to be 4. When x is equal to 2, this is going to be x to the third power over 4 squared. 4 squared times 2 to the fourth power. And we know this, of course, is 16 times 16, which would be 256. But I'll just leave it like that for now. Plus, when x is 3, this is going to be x to the fourth over 4 to the fourth power times 4 to the fourth times 4 to the fourth. So it's really going to be 4 to the eighth power. And we'll just keep going on and on and on just to get a sense of what this function would look like, this function that's defined by an infinite series. Now, what I'm curious about is for what x values will this function converge to finite values? Or another way of thinking about it, let's come up with the radius of convergence or the interval of convergence for this function. Now, since we've just been talking about the ratio test, you might say, well, maybe the ratio test is useful. For what x values is this thing going to converge? So let's apply the ratio test. So let's take the limit as n approaches infinity of the absolute value of the n plus 1th term over the nth term. And so for this particular case, this is going to be the limit as n approaches infinity. So the n plus 1th term, I'll do this in orange. So it'll be x to the n plus 1 plus 1. So it's going to be x to the n plus 2. So it's going to be x to the n plus 2 over 4 to the n plus 1, 4 to the n plus 1 times n plus 1 to the fourth power. And we're going to divide that by the nth term, which is just going to be x to the n plus 1 over 4 to the n times n to the fourth, which of course is going to be the same thing as the limit as n approaches infinity of, I can just copy and paste this, of this. So copy and paste that times the reciprocal of this. If we're dividing by a rational expression, that's the same thing as multiplying by the reciprocal. So times 4 to the n to the fourth over x to the n plus 1 power. Actually, let me just clean this up a little bit. Now, can we simplify this? Well, x to the, let me get another color here. So x to the n plus 2 divided by x to the n plus 1. Well, n plus 2 minus n plus 1 is just going to be 1. So this is just going to simplify to an x in the numerator. And then let's see, 4 to the n divided by 4 to the n plus 1. So this is the same thing as, this is the same, if we divide the numerator and denominator by 4 to the n, this is going to be a 1. And this is just going to be a 4. So this is going to simplify to, I forgot my absolute value signs, don't want to do that. So let's keep my absolute value signs here the whole time. This is going to be equal to the limit as n approaches infinity of the absolute value of, we're going to have x n to the fourth in the numerator. So let me write that down. We're going to have x times n to the fourth in the numerator. And in the denominator, I'm going to have 4 times n plus 1 to the fourth. Well, what's that going to be? Well, if you expand out n plus 1 to the fourth, it's going to be n to the fourth plus a bunch of terms, and a bunch of lower degree terms. This is going to be the highest degree term. So if you distribute the 4, it's going to be 4n to the fourth plus a bunch of lower degree terms. So let me write it that way. So it's over 4, I'll use the same colors, 4n to the fourth plus a bunch of lower degree terms. Now, what's the limit as n approaches infinity here? Well, we have the same, we want to look at the highest degree terms. We want to look at the n to the fourth degree terms. And so it's really going to be the coefficient on these. And one way to think about it, if you divide the numerator and the denominator both by n to the fourth, these are the only terms. You're going to have an x in the numerator, and the denominator you're going to have a 4, and all these other terms are going to be divided by some power of n. So as your limit approaches, as n approaches infinity, all the other terms are going to go to 0, and all you're going to have left in the denominator is a 4 and an x in the numerator. So this right over here, the limit as n approaches infinity is going to be x over 4. Or I should say the absolute value of x over 4. So it's going to be equal to the absolute value of x over the absolute value of x over 4. And now we can apply the ratio test, or I guess we were always applying it, but now we can really do the test part of it. And the ratio test tells us that if this limit right over here, as long as it evaluates to something that is less than 1, then our series will converge. And so we just have to say that this expression right over here has to be less than 1. So our function is going to converge to finite values as long as the absolute value of x over 4 is less than 1. And this is dividing the absolute value of, or the absolute value of x over 4 is going to be the same thing as the absolute value of x divided by 4, since 4 is positive, so that just has to be less than 1. Multiply both sides by 4, won't change the inequality since 4 is positive. So you're going to have the absolute value of x has to be less than 4. And so just like that, we have defined the radius of convergence. This right over here is the radius of convergence for our function, or for our infinite series. Radius of convergence. Or if we wanted to write that same information as an interval of convergence, we would say that x has to be less than 4 or greater than -4. This is the same information right over here. Expressed this way, this is the interval of convergence. Interval of convergence. So these are the x values for which this original function here is going to converge to finite values.